Hello, everyone. I hope you're all safe and sound. Welcome to the 13th lecture on analog and digital electronic circuits, in which we will study small signal models for MOSFETs. So after introducing the small signal approximation, I will discuss different expressions for the small signal transconductance of a MOSFET, and then we will construct small signal models for an NMOS device. We will also study this phenomena, which is called channel length modulation, which makes the drain current a function of the drain to source voltage in the saturation mode of operation. And then we will use the expressions derived in this respect, in this regard, by taking into account the channel length modulation effect to augment the small signal models. So we know that in saturation mode of operation, a MOSFET behaves like a voltage controlled current source, and its drain current, which is also called the saturation current, is given by this quadratic dependence on the gate to source voltage. And because of this quadratic dependence, we can see that the voltage current characteristics, they are nonlinear. So in order to ensure that the resulting amplifier behaves like a linear circuit in which the output is a linear function of the input, we must model NMOS as a linear device first. So assuming that the small signal which is to be amplified by the NMOS amplifier is labeled as V small gs, assuming that small signal has a sinusoidal time dependence, then NMOS must be biased by a proper DC voltage source, which is given by this capital V subscript capital GS, to ensure that the device remains in the saturation mode for the entire cycle of sinusoidal cycle of the small signal VGS. So this diagram here, this circuit shows the excitation of the amplifier with the small signal VGS, and this capital VGS is here only to bias the NMOS in the saturation mode of operation for the entire cycle of the small signal. So the total gate to source voltage then is given by small v subscript capital GS, and it is the sum of this biasing input voltage and the small signal which is to be amplified, which results in the total drain current given by the same quadratic equation as I showed before. So the total drain current has quadratic dependence on the total gate to source voltage. The bias point is found by setting the small VGS to 0, because the bias point, which is the DC component of the drain current and the drain to source voltage, this bias point is actually the response of the circuit to the input biasing voltage VGS, capital VGS. So we find that bias point by setting small VGS to 0 by short circuiting this source, which makes the gate to source voltage equal to capital VGS. So simply replacing this small subscript capital GS with capital VGS, we get the DC component of the drain current. And by writing a KVL for the output loop, we can find the DC component of the drain to source voltage, which is given in turn by this equation. So if we expand the total drain current, which was a function of the total gate to source voltage, which is the sum of the DC component of the gate to source voltage and the AC component of the gate to source voltage, then we can separate out the DC and AC terms. When I open the square, I can separate out this DC term from this AC term. So by rearranging the terms, I get this equation. So here I have replaced this component with ID, because we can recognize this as the DC component of the drain current. So this is the response of the MOSFET to the DC voltage VGS. So this we have called this the DC component of the drain current. So by replacing this term with ID, this is what we get. So we can see in this equation that this second term is the cause of non-linearity, because this introduces this makes ID a quadratic function of the small signal VGS. So if we ignore this term in comparison with this term, that is, if we assume that the second term is much, much smaller than the third term, then we get the resulting small signal approximation for the MOSFET. So that says that the AC component of the gate to source voltage should be much, much smaller than twice the overdrive voltage at under DC settings. So this VGS minus V threshold is the overdrive voltage corresponding to the DC biasing voltage at the input. So this gives us the small signal approximation for the MOSFET. So under this approximation, I can ignore this second term and approximate the drain current with the sum of these two terms. So we can see that this equation is although an approximation, but it gives the drain current as a linear function of the small signal gate to source voltage. So we call this term, the second term, as the response of the MOSFET to the small signal small VGS, and we call this the small signal drain current of the amplifier. And it is given by the product of the MOSFET transconductance parameter, the overdrive voltage at DC biasing VGS, DC input voltage VGS, and it is also determined by the small signal gate to source component of the voltage, small signal component of the gate to source voltage. So we call this term, we refer to this term as the small signal drain current of the amplifier, in which further we refer to this term, which is the product of the MOSFET transconductance parameter and this overdrive voltage, as the MOSFET transconductance, and we denote it by GM. And from this expression, you can see that it is given by the ratio of the small signal drain current to the small signal gate to source voltage. So the MOSFET transconductance is defined as the ratio of small signal drain current to small signal gate to source voltage, and it is given by the product of MOSFET transconductance parameter and capital VGS minus V threshold. So, and this is the reason why Kn is called the MOSFET transconductance parameter, because it defines the transconductance for the MOSFET. So we can see that because it is given by the ratio of the small signal drain current to the small signal gate to source voltage, we can see that this ratio is equal to the slope of the ADE VGS characteristics. We can mathematically verify it by differentiating the expression for the total drain current, which is given by half times the MOSFET transconductance times total gate to source voltage minus V threshold whole square. And if we differentiate this total drain current with respect to the total gate to source voltage at the bias point, because this is a non-linear expression. So if I go back, then this expression is non-linear. So if you want to find the slope of this with respect to VGS, we'll have to find it at a particular point. So if I differentiate this expression with respect to VGS at the bias point, then it is very easy to show that the result is given by GM. So you can differentiate it, and you'll find that the slope of this curve is given by Kn times capital VGS minus V threshold, which is GM. So this verifies that GM, which is given by the ratio of the small signal drain current to the small signal gate to source voltage, is indeed equal to the ratio, is equal to the slope of the ADE VGS characteristics, which are shown here in this diagram on the right. This parabolic curve shows the ADE VGS characteristics, and GM is the slope of the ADE VGS characteristics at the bias point. So in other words, GM is the slope of the straight line, which is tangent to the curve, which represents the ADE VGS characteristics at the bias point Q. So this black line here is the tangent to the blue curve at the bias point Q. So the slope of this black line, which represents the slope of the characteristics at the bias point, is equal to GM. So here I have also shown the amplification obtained at the output in terms of the drain current. So on top of the characteristics, I have shown the total drain current. So The DC component of the drain current, capital ID, is given by this vertical black line. I'm sorry, is given by this horizontal black line. So the DC component, which is capital ID, is given by this black horizontal line, and the DC component of the input gate to source voltage, which is capital VGS, is shown by this vertical line, this vertical black line. So Q here is the bias point, which gives us the DC component of the input voltage and the DC component of the output drain current. So here Q shows the DC component of the input voltage and the DC component of the output drain current. So on top of this vertical line, which shows the DC component of the gate to source voltage, I have shown this sinusoidal signal, which is the small signal VGS. So small signal VGS plus capital VGS gives us the total gate to source voltage. So this sinusoidal waveform riding over DC is actually the total gate to source voltage. So the MOSFET, the NMOS amplifier, then produces the total drain current, which has sinusoidal dependence. So this sinusoidal waveform is GM VGS. This is the small signal drain current. This sinusoidal waveform is the small signal drain current riding over capital ID, which is the DC value. So you can see that this straight line, this black straight line, which is tangent to the MOSFET at point Q, under small signal approximation, very closely models the operation of the nonlinear device. So what small signal approximation does is that it limits the instantaneous value of the total gate to source voltage to such a portion on the curve, which can be very closely modeled by the straight line. So these dotted magenta lines, both vertical and horizontal, they give us a region of the ID VGS characteristics, which is very well approximated by this straight line. So this is the essence of the small signal approximation, that it keeps the instantaneous voltage, it keeps the small signal AC component riding on top of the DC value, limited to such a portion of the curve, which is very well approximated by the straight line. So this is what this is the graphical explanation of this approximation. That the resulting response, which is the drain current, which follows this very, very well approximated straight line region between this point and this point. So the response to this VGS is ID, which follows this portion of the curve, which is very well approximated by the straight line, which is tangent to the curve at point Q, and hence we get a linear output. So an output which is just a scaled version of the input. So such an output is a linear function of the input. The input is just stretched and amplified and appears as the output. So this is the graphical explanation for the small signal approximation of the MOSFETs. That the overall gate to source voltage is limited to within the instantaneous value is limited to within the region of the curve, which is very well approximated by the straight line. So from this definition here, we can see that this is one of the expressions for the MOSFET transconductance, in which I have written Kn, which is the MOSFET transconductance parameter in terms of process transconductance parameter and the aspect ratio. So Kn is Kn prime times the W/M aspect ratio. So this is one of the expressions. Here I've just replaced this capital VGS minus V threshold with capital VOV. So this is the overdrive voltage corresponding to the DC gate to source voltage. So from the from this equation in 4, we can see that ID is 0.5 times Kn prime W/L times VOV square. So we can rearrange this term and replace VOV with 2 times ID over Kn prime W/L square root, and then simplify to get this expression. So this expression relates GM with the MOSFET transconductance and the drain current. This expression relates GM with the MOSFET transconductance parameter and the overdrive voltage, and this expression relates GM with the MOSFET transconductance parameter and the drain current. Furthermore, from the same expression of the saturation current, DC component of the saturation current, we see that Kn prime W over L is 2ID over VOV square. So we can replace in this expression, we can replace Kn prime W over L with 2ID over VOV square, and VOV will get cancelled with the square and will be left with 2ID over VOV. So this expression relates the MOSFET transconductance with the drain current and the overdrive voltage. So we've got three expressions. The first one relates the MOSFET transconductance with the MOSFET transconductance parameter and the overdrive voltage. The second one relates GM with the MOSFET transconductance parameter and the drain current at the DC component of the drain. And the third expression relates the MOSFET transconductance with the DC component of the drain current and the overdrive voltage corresponding to the DC VDS. So from these three expressions, we see that in order to increase the MOSFET transconductance, we must use a device which has a larger aspect ratio, which has a larger W over L. So in order to increase GM, we must use short channel and wide device. In other words, we must use a device which has greater W over L value. Or we can equivalently, in order to increase GM, we can equivalently increase the DC component of the gate to source voltage VGS. However, if we increase the DC component of VGS, then the DC component of the drain current is increased, and as a result, the voltage at the DC component of the voltage at the drain, which in this case is also equal to VDS, and is given by VDD minus capital IDRD. So increasing the DC component of gate to source voltage, increasing the DC component of drain current ID, which in turn decreases the DC component of the voltage at the drain, which is equal to capital VDS. So increasing capital VGS decreases capital VDS, and hence, as far as the output voltage swing is concerned, since capital VDS is decreasing, the swing on the negative side is reduced, which in turn decreases the overall maximum symmetric swing of the output voltage. So increasing capital VGS has a disadvantage of reducing the voltage swing, maximum symmetric voltage swing of the amplifier. So this must be kept in mind. So now we know that the gate terminal does not draw any current. So the DC component as well as the small signal AC component, due to the small signal VGS, they are both zero, which means that the total gate current, which is the sum of the gate currents due to the DC gate voltage, gate to source voltage, and the AC gate to source voltage, which are labeled as capital IG and small IG respectively. So the total gate current, which is the sum of these two components, is zero. So if we consider the gate to source terminals as constituting a port, then we take the direction of small IG such that it enters the gate terminal. Although its value is zero, but when we draw the circuit, we draw small IG or total IG as entering the gate terminal with magnitude zero. So the small signal gate current, small IG, enters the gate terminal, which is the positive terminal of this gate to source port. Hence, and the voltage between the gate to source terminals, or the voltage across this port, is small VGS. So the ratio of this small signal gate to source voltage VGS to the small signal gate current which enters the gate terminal, which is the positive terminal of the gate to source port. This ratio defines the resistance between gate and source terminals looking into the gate. And since this current small IG is zero, this resistance is infinity. So the small signal gate to source resistance looking into the gate, which is denoted by R subscript small gs, is the ratio of the small signal gate to source voltage to the small signal gate current. And since small signal gate current is 0, this resistance is infinite. Furthermore, we know that since there is no gate current and the current which flows from the drain towards the source through the channel, through the conductive channel, we call it the drain current, but that is also equal to the source current. So the source current is equal to the drain current, and the drain current has two components, the DC component and the AC component. So we take the DC component of the drain current to be equal to the DC component of the source current, and the small signal AC component of the drain current to be equal to the small signal AC component of the source current, like this. So small signal AC component of the source current is also given by GM/VGS because the drain and source currents, they are the same. So if we consider the gate to source voltage again as constituting a port, then the source current IS leaves the source terminal of the port. In other words, minus IS enters the source terminal of the gate to source port. So the ratio of the gate to source voltage, the ratio of the source to gate voltage, which is equal to minus VGS. So if we take in this case now the source terminal as being positive with respect to the gate. In other words, if I measure the voltage at the source with respect to the gate, and instead of taking the source current coming out of the source terminal, if I assume minus IS going into the source terminal, then the ratio of the voltage between source and gate, which is VSG, divided by the current entering the source side of the port. This defines the resistance seen looking into the source terminal between source and gate. So again, and is denoted by R subscript S. So R subscript S is the ratio of the voltage of the source terminal with respect to gate to the current entering the source terminal. So it is the ratio of VSG to minus IS, because IS leaves the source terminal, minus IS will enter the source terminal. So this by definition gives us the resistance seen looking into the source between gate and source terminal. And since VSG is equal to minus VGS, so this minus gets cancelled with minus in the denominator. So this resistance is equivalently given by the gate to source voltage divided by the source current. And from this equation, we can see that the ratio of VGS to IS is 1 over GM. And GM is MOSFET transconductance parameter times this factor. So it is 1 over Kn times this factor. So the small signal resistance looking into the source between gate and source is given by 1 over GM. So using these relations, that is using this relation which gives us the small signal drain current of the NMOS device, and using this information that small signal gate current is 0, and using this information that the small signal source current is equal to VGS by RS. So VGS by RS is small signal drain current, the small signal source current. And since 1 over RS is GM, so IS is again equal to GM VGS, which gives us again, which reinforces the fact that source current is the same as the drain current. So using these three equations, we can construct this hybrid pi model for the NMOS device. So in this model, this open circuit between gate and source tells us that the resistance seen looking into the gate between gate and source is infinity, which is why the small signal gate current is 0. And the drain current, which is equal to GM VGS, is also equal to IS. And here I've also shown the voltage between drain and source. So this model is the output of these relations. Similarly, we can rearrange these relations such that we can write GM VGS, since VGS from this relation is equal to IS RS. So we can write GM VGS as GM IS RS. And since RS is 1 over GM, so we can again see that ID is equal to IS. IG is 0, and we can write IG from this relation as VGS over RGS. So RGS is infinity because IG is 0. In other words, since RGS is infinity, IG is 0. And then we can write IS again from this equation. IS is equal to VGS over RS. So using these three equations, we can construct a slightly different model for the MOSFET, which is called the T model, small signal T model for the device, in which the drain current is given by GM VGS and is equal to the source current because the gate current is 0. So if I write KCL here, this current is 0, so this current must be equal to this current. So this, I call this the drain current, and this is the source current. And the source current IS is given by VGS over RS. So since the source current is passing through this resistance, the voltage across which is VGS, so this resistance must be RS. Or in other words, this resistance should be 1 over GM. So IS is GM VGS. Or in other words, IS is VGS over RS. So RS is 1 over GM. So ID is equal to IS, which is given by VGS divided by 1 over GM, which is equal to VGS times GM. So this set of equations gives us this slightly different model, which we call the small signal T model of the device. So since these two set of equations, they are exactly equivalent to each other, these two models, they are exactly equivalent to each other. So one may use this model or this model to model the underlying device as a linear circuit and the resulting amplifier as a linear circuit as well to find other small signal parameters. So far, we have assumed that the drain current is independent of the drain to source voltage in the saturation mode of operation, but and is a constant. But in practice, this is not the case. So if we review the channel pinch-off phenomena, then what happens is that when VDS becomes equal to VOV, which is VGS minus V threshold, then the voltage between gate and drain drops to V threshold. And at that point, the depth of the channel at the drain, it reduces to 0. So there is no channel at the drain. This we call the channel pinch-off phenomena. That is, the channel at the drain gets pinched off. And we said that increasing VDS beyond VOV does not change the shape of the channel, and hence the drain current remains the same. But if we look closely, then increasing VDS beyond VOV will reduce the voltage between gate and drain below V threshold. Now, since the voltage between gate and any point X in the channel, it increases as we move from X is equal to L to X is equal to 0. So at the onset of saturation, VGX, the voltage between G, the gate, and any point X along the channel, is equal to V threshold when X is L, and it increases from V threshold to VGS when X is equal to 0 at the source side. So the voltage between gate and X, which is the point in the channel, it increases from the drain side as we move from the drain side towards the source side. So when the voltage as we increase VDS beyond VOV, then the voltage between gate and the drain, it drops below V threshold, which means that there will come a point to the left of the drain at which the voltage between gate and that point is equal to V threshold. I have labeled that point by L1. So here I'm assuming that that VDS is increased beyond VOV to such a value that VGD drops below V threshold and VGX at X is equal to L1 becomes equal to V threshold. So now, since the voltage between G and X is equal to L has dropped to V threshold, the channel pinches off at X is equal to L1. So the voltage between G and X is equal to L1 has now dropped to V threshold. This means that at X is equal to L1, we will observe the channel pinch off at X is equal to L1. So this reduces the length of the channel, if you can see. So the length of the channel, the effective length of the channel has been reduced from capital L to capital L1, where the difference is given by delta L. So this phenomenon is called channel length modulation, in which increasing VDS beyond VOV moves the channel pinch off point towards the source, hence reducing the effective length of the channel. So here I've also labeled the voltages. So we know that the voltage at the gate with respect to source is VGS, and the voltage at gate with respect to any point X, which is denoted by VGX, is given by VGS minus Vx. So when VGX is V threshold, then the voltage X is given by VGS minus V threshold. So the voltage now here at this point with respect to the source where the channel gets pinched off is given by VGS minus V threshold. Or in other words, the voltage of this point with respect to the source is equal to the overdrive voltage. And since the voltage between drain and source is equal to VDS, the voltage between drain and the point at which the channel gets pinched off is given by VDS minus VOV. So the voltage between drain and the point at which the channel pinches off is equal to the additional voltage beyond VOV, additional voltage of additional VDS beyond VOV. So the voltage at drain with respect to this X is VDS minus VOV, which is additional VDS beyond VOV. So since the drain current is inversely proportional to the length of the channel, as the length of the channel is decreased, the drain current will increase. So the drain current is not exactly constant in the saturation mode. As the length of the channel decreases, the gate current will increase. So increasing VDS beyond VOV will further move the pinch off point towards the source. Hence, it will further decrease the length of the channel, which means that it will further increase the drain current. So increasing the drain to source voltage will increase the drain current because the effective length of the channel will keep on decreasing with increase in VDS. So instead of taking the decrease in the length of the channel into account, we model this channel length modulation effect through this factor here of 1 plus lambda VDS minus VOV. So VDS minus VOV is the additional VDS beyond VOV. So when VDS is equal to VOV, this term is 0. This means that since VDS minus VOV is 0, so this point, channel pinch off point, is the same as the drain side of the channel. So this point is at the drain, which means that we are at the onset of the saturation mode of operation. And as VDS goes beyond VOV, VDS minus VOV becomes greater than 0, and the point at which the channel gets pinched off moves towards the source. So this factor, as the channel moves towards the source, this factor will increase. So lambda times this factor will increase, which will take into account the increase in the drain current beyond its saturation value as VDS decreases and as effective channel length decreases. So this factor here, this factor takes into account the effect of channel length modulation by keeping the length of the channel the same in the expression and including and modeling the increase in ID through this term. So this factor models the increase in ID by keeping the channel length in the expression the same. So since and also this factor is almost always approximated by this term. So we will approximate the drain current in the saturation mode by this factor of 1 plus lambda VDS. Since this term here already corresponds to the value of the saturation current, so it has dimensions of the current, which means that this term should be dimensionless, which in turn means that since VDS has units of volts, lambda has dimensions of 1 over volt. So lambda is not only a process dependent parameter, but it is also a device dependent parameter. As I will show in a minute, lambda has an inverse dependence on the channel length of the device. So this statement can be verified by looking at the circuit, the diagram, the cross-sectional diagram of NMOS again. So beyond VOV, when VDS increases beyond VOV, then the point at which channel gets finished off moves to the left, and this decreases the effective length of the channel. So instead of modeling this effect through this factor, we could model the increase in drain current by the decrease in the channel length. So when VDS is such that the length of the channel is equal to L1, as shown here in this diagram, which is less than L, then the drain current is given by this expression, in which I have replaced L with L1, where L1 is L minus delta L. So this expression is exactly equivalent to this expression. The only difference is that here we keep L the same and include the same effect as obtained here by the decrease in channel length with this term. So, but here instead of using that term, I have actually reduced the length of the channel. I have done so to show you that why lambda is inversely proportional to the length of the channel. So in this case, we can see that the drain current, which is given by this expression, depends on L and delta L. So if we have two devices, and if the operating conditions are exactly the same, that is the VDS is beyond VOV is the same for the two devices, then delta L is the same for the two devices. But the device with the smaller channel length will have larger ID than the device with larger channel length. In other words, the corresponding increase in ID will be greater in the device with shorter channel length than in the device with longer channel length, which means that the effect of channel length modulation is more pronounced for shorter channel length devices. And since this effect is actually taken into account by this factor here, this factor is actually included to model the increase in the drain current. So, and since we have just established that the channel length modulation effect is more pronounced in short channel devices, lambda must be a larger value in case of short channel devices than for longer channel devices, which is why lambda is inversely proportional to the channel length, because lambda, since channel length modulation is more pronounced in shorter channel devices, lambda should be larger for shorter channel devices. So reducing the length of the channel increases lambda, because reducing the length of the channel increases the effect of channel length modulation, as can be seen from this equation here. So here I've shown the ID VDS characteristics for different values of VGS, but this time I have taken into account the channel length modulation. So I have plotted this equation here. So I've taken into account the effect of the dependence of ID on VDS. So by increasing VDS at a fixed VGS, ID can be seen to increase. So all of these different curves which correspond to different VGS values, when we extrapolate them backwards, then they can be seen to intersect at approximately the same point. I say approximately because we can find this intercept actually. So this intercept is found by setting the drain current, total drain current to 0. And the total drain current is 0 when this new factor is equal to 0. So I call this voltage at which the drain current goes to 0. In other words, I call this voltage at which the curves, they intersect intercept the x-axis as the early voltage. And I denote its magnitude by a VA. And it is named after James Early, who discovered a similar phenomena of base width modulation for BJT, which makes the collector current a function of collector to emitter voltage in the active mode of operation. So from that reference, it is called the early voltage and is represented by VA. So ID goes to 0 when VDS is equal to minus VA, because the magnitude of this voltage is VA, so this value is actually minus VA. So when this term is put to 0, then minus VA can be seen to be equal to this factor. So VOV, since VOV is different for different curves because it depends upon VGS, so this point minus VA is different for different curves. But it is, like I said, if we use this approximation, which is most commonly used, then using this approximation is equivalent to ignoring this VOV, which gives us the early voltage as equal to 1 over lambda. So you can see that almost all of these curves, they intersect or intercept the x-axis at approximately the same point. This intercept is approximately the same for all of these curves, and it is given by minus 1 over lambda. So the magnitude of this point, which is called the early voltage, is equal to 1 over lambda. And since lambda had units of 1 over volts, so VA has the dimensions of volts. And since lambda was inversely proportional to the channel length, VA is directly proportional to the length of the device. And hence it can be written in terms of the length of the device like this, in which this constant here, VA prime, this is a process dependent parameter. And it is typically specified in volts per micron and has a typical range of these many volts per micron. So including the channel length modulation now, I go back to the actual drain equation. So in this drain current equation in the saturation mode, where we include the channel length effect of channel length modulation, if I again apply the small signal approximation to this saturation value, then this saturation value can be written as an approximate sum of the DC component of the drain current and a linear function of small VGS. So here I've written the quadratic term under small signal approximation as the DC component of the drain current plus GM times small VGS. And I've also included the effect of channel length modulation. So I can multiply the two terms, and then I can ignore this term here. Because lambda is inversely proportional to, lambda is equal to 1 over VA, because VA is 1 over lambda. So lambda VGS VDS is actually equal to VDS over VA times VGS. And typically VA is greater than VDS. So VDS over VA is less than 1. And small VGS is already smaller, is a small quantity. Then their product, small VGS times VDS over VA is even smaller. So this term can be ignored. And we approximate the drain current as the sum of these four components, in which the response of the drain current to the small signal drain to source voltage, which is given by this term, is called small ID comma DS. So this is the small signal drain current due to small signal drain to source voltage, and is equal to capital ID times lambda times VDS. And from this equation, we can see that the ratio of VDS to ID comma DS is equal to 1 over lambda ID. And since 1 over lambda is VA, so it is equal to V over ID. And this is called the small signal resistance between drain and source looking into the drain terminal, because it is the ratio of the voltage between drain and source. In other words, it is the ratio of voltage of the drain with respect to the source to the current entering the drain terminal. So this by definition defines the resistance, which we call R0. And R0 is the small signal resistance between drain and source looking into the drain, because we are dividing it by the drain current, which corresponds to, which is the response to the drain to source voltage. So VDS over small ID comma DS is equal to R0, which is defined as the small signal resistance between drain and source looking into the drain terminal, and it is given by VA over ID. And this resistance can also be seen to be equal to the inverse of ID VDS characteristics. So if I take the derivative of ID with respect to VDS at the bias point, so I differentiate the actual expression of ID with respect to VDS at the bias point, I can find it to be equal to lambda times ID, which is equal to 1 over R naught. So R naught is actually equal to the inverse of the slope of the ID VDS characteristics at the bias point. So replacing R naught with this value in this expression, we can write the drain current as an approximate sum of. So we can write this expression as the sum of the DC component. So this ID is the DC component of the drain current without taking into account the channel length modulation, and this here, which is lambda times ID, is 1 over R naught. So VDS over R naught is the addition to the DC component of the drain current due to the channel length modulation. So this is the modified DC component of the drain current. And similarly, VDS over R naught, which is when added to the small signal drain current, gives us the new small signal drain current, which is a function of the small signal gate to source voltage and the small signal drain to source voltage. So this is the modified DC component, and this is the modified AC component of the drain current. So we can use this relation to augment the small signal hybrid pi and T modules. So everything else remains the same. So the drain current, gate current is still 0. Drain current is still equal to this source current. Previously, the drain current was given by GM/VGS, but now we have a new component to the drain current, which is given by VDS over R naught. So this is an ohmic relation. So it must be modeled through a resistor. So we can see that the drain to source voltage divided by R naught gives us the component of the current, gives us the current flowing through R naught. So VDS over R naught is the current through R naught, and GM/VGS plus VDS over R naught gives us the total drain current, which is in compliance with this relation. Similarly, we can augment the T model as well. So again, gate current is 0, which means that the drain current is equal to the source current. However, now the drain current is the sum of two components. So GM/VGS plus this ohmic component. So VDS divided by R naught. Since VDS is the voltage across R naught, so VDS divided by R naught gives us the current through R naught, which when added with GM/VGS gives us the total drain current. And the total drain current is equal to the total source current, because the current through 1 over GM is actually VGS over 1 over GM, which gives us GM/VGS again. So this current is GM/VGS. This current is VDS over R naught. So the sum of these two currents, which is equal to the drain current, is also equal to the source current. So again, this model is in compliance with this component, new small signal component of the drain current. So this is how we include the effect of channel length modulation and the dependence of the drain current on the drain to source voltage. So this brings us to the end of this lecture. Thank you very much for your time, and I will see you in the next class. Take care.